So it's unfortunate that I still deal with parents and students that don't get this, but students understand, parents I don't. If you're encouraging your kid to avoid daily repetitive tasks, you're actually hurting them. And I know when I said daily repetitive, there are no shortcuts, so I want you to accept that right away. There are no shortcuts. However, if you do what I'm suggesting, it's much faster than any other method. The worst thing you can do is leave things to the last week, and that's human nature. So we have to find a way to avoid human nature. You build a good habit over 60 days, so I want you to start small. It can be 5 minutes, 10 minutes, anything that you can achieve daily. And it's not 5 minutes of sitting in front of this computer screen, it's 5 minutes of this. Writing and solving problems will get you 80% in math much faster than anything. And yeah, you might say, well, I don't know the method to solve that. Well, that's part of this video. But it's also very easy to YouTube anything in any high school textbook, and somebody can explain it in 5 minutes. Then you just have to repeat their steps. But this is the best way to remember what you watched in that YouTube video. Keep 3 notebooks. A master notebook that will have each section and concept copy and pasted, and then 2 to 3 examples. If you handwrite or type them yourself, these examples, you will remember it 90% more effectively. Okay? Then you got to have a problem-solving notebook where you do questions like we're doing in this video, so that later on, when you're studying for the test, your teacher is going to use questions from or questions like this textbook. So why not keep a record of them so you don't have to do them twice? Because believe me, if you do a week of chapter 1 and then move on to chapter 2 and chapter 3 and chapter 4 and have to come back to chapter 1, you're not going to remember it. But you will remember it once you see what you wrote in the notebook. Finally, you got a third notebook where you just do rough notes from class, chicken scratches, and rough calculations. Keep these notebooks separate. Don't do chicken scratches in your master notebook, and don't do master notes in your problem-solving notebook. Finally, use your tools. You live in an information age. Desmos, Symbol Lab, graphing calculators. They all speed it up. You're not, it's boring. So is failing. So is repeating a class. So is getting stuck in a job that required some skills that you now realize you could have learned easily just by doing 15 minutes a day. So that's unfortunately going to be something at the beginning of all these videos. So we're going to go on to section 3.2 and, wrong one. And 3.2, and we'll close that other one, is all about maximum and minimum intervals. And before you do anything, I want you to realize if you're on a graph, if you have a normal Cartesian graph, and you're dealing with a graph that has a finite beginning and a finite end, say to there, this section is about trying to find this maximum and this minimum, because at those points we know the slope of the tangent is 0. In other words, the slope of the first derivative is 0. However, please note, this is what's called a sort of local maximum, which means it's just the maximum around this area. Note that this dot over here is higher than this. This is the actual maximum. This solid dot means we're not measuring anything more beyond this domain, from this x value to this x value, this solid dot as well. Please note, though, that this one is not the lowest point. This is not the lowest point. This is right here. So in this graph, we have a maximum part of the curve here that is not the maximum. This is the maximum over here. That is not the maximum, sorry. This is the maximum over here. But we have a low part of the curve that is the minimum. So when you're testing for maximum, minimum, and the thing has a finite domain, don't forget to plug in the values here into the main function to see if they are lower than this part or higher than this part. Because in your question, this might actually be the maximum. And if you answer that, you might answer incorrectly. So that's the trick in this section. However, For graphs that go on forever and ever, they start, way up in infinity and end up way down in infinity. These are the minimum and maximum that we're looking for. Because, we know that goes on, that the little arrow say it goes on forever. We're concerned about here. So they tend to call these local max or critical points or turning points. And turning points make sense because here, look, the slope is negative, negative. We have this point where slope is 0. Suddenly the slope is positive, positive, positive. Then this turning point and negative, 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 negative forever. We're also going to learn something called the second derivative because at some point during these slopes, they must turn around, right? If you're on a ski hill, it's not steep there. It's getting really steep here, and then it's getting less steep there. This point where it went from really steep to getting less steep is called an inflection point. And we're going to discover that when the second derivative equals 0, that's where that happens. It's essentially, in terms of motion, it's when acceleration starts going from negative to positive, or from positive to negative, depending on what your slope looks like. It's when the second derivative starts going from positive to negative. And we're going to learn more about that. And the more you study these things, the more you graph them, the more visually you'll get them. Okay? Here we go. So we're going to jump straight to what the lesson is. So there's what I was talking about. And that's one thing right there. Boom. Put that in the master notes. All right. Keep going. That gives some examples, how to solve them. And you know what? You can just jump straight to questions. You don't have to read these. And then they explain that when we take the derivative and the derivative is equal to 0, you're going to find the max. And boom. We used to find the max of parabola. How? Completing the square. So this is a better sort of technique. Sometimes you can't complete the square. Don't forget to also go to your early, and I kind of skipped that here. Don't forget to get to your skill sets that are needed for the chapter. And look at that, I jumped all over the place. You're going to need that. They'll always review certain skill sets. I see that they haven't done that here, but they usually go over completing the square and parabolas and all that stuff. State within the reasons why the maximum rule cannot be used to determine the maximum. So state why we couldn't use the derivative to find this. Why or why not? Well, that's a cubic curve. And then there's a limit on the domain. We can most certainly use this cubic curve to find it. The slope 3x squared minus 10x is the derivative slope. Now perhaps there's a trick I'm not missing, but if we take the derivative of this, we should find it, because that's just a cubic, and it's a positive cubic, so a positive cubic starts in quadrant 3, does a wiggle, ends in quadrant 1. Sometimes it doesn't do a wiggle, sometimes it does that perfect thing. That would be the perfect x cube, and that's sort of a triple wiggle. And of course, if it's this, we're not really going to find it. So looking at this, let's factor out x squared. And, sorry, we can't factor out x squared. Let's take the derivative first. 3x squared minus 10x. Okay, what is that? That's a parabola, right? Let's set that to 0 and first factor out an x. We get 3x minus 10. And we're going to set it to 0. So clearly at 0, 0, at 0, this would be derivative, so there's something going on at 0. We don't know what the value is once we plug 0 in. It's actually 10. So at 0, 10, let's get rid of this graph. At 0, 10, we got something going on. Where else do we have something going on? Makes sense, because when x is 0, right? That's how we find the y-intercept. And where else is 0 going on? Well, when this thing here is equal to 0. Right? Okay. When x is equal to 10 over 3, or 3 1/3. So when you plug that in, you're going to discover another value. And the question is this a max Is this a min? And here I'm going to tell you right away. I don't know where this 3x, where this third is, but I do know it's to the right of this 0x. It's over here. And I also know cubics go up, and then when they hit the turning point, they turn around. So that means somewhere here is going to be the min, and somewhere there, that's going to be the max. So yes, we can use it. I would then plug in 3.5, and I'm just going to roughly do it, not accurately. It's going to be about 30. It's going to be about minus 45, maybe 50. It's going to be plus 10. So it's going to be about minus 10 right down there. And indeed, I found the min. If I took the second derivative and set it to 0, I will find the one inflection point in this graph. And you're going to discover parabolas have no inflection point. Cubics have 1. To the 4 can have up to 2. The 5 can have up to 3. And 6 can have up to 4. So it's always 2 less than the term, at least for polynomials. What about this one? Well, it helps if you understand your graphs. So I'm going to just get rid of as much garbage as I can, as a matter of fact. Let's take it to a new screen. What about this one? Well, you've got to recognize your graphs. Look at the bottom. There's an asymptote, right? Where is the asymptote? It's at x is equal to 2. Is there anything bizarre going on up here? No, no. So that's going to be a horizontal asymptote at the x-axis, which means we're dealing with something that either looks like this or looks like that. These graphs don't have maximum and mins. They start here close to the asymptote, they slowly climb and reach the other asymptote. Same with here. They want to be just a normal graph. They want to be like a line. It wants to be this. But when it reaches the asymptote, this one starts doing that. And then this one does something like that. And then here they continue being this line, 3x. But when they reach this point, they can't continue their journey and they zip around. But notice they don't have an official maximum. And that's why that one doesn't have a max. I don't know how much time I'm going to spend on this early stuff, because it's just a waste of time. What about this one? Don't leave. So what about this one? This one's slightly different. The bottom's always going to be positive, and the top's going to fluctuate between negative and positive. And we also see that when x is smaller than plus or minus 2, we have an asymptote. So we're going to have some weird graph that probably, so I'm talking about this one now, that probably if I was going to measure, so we have this weird zone in the middle, and I believe it might have a maximum because we have two asymptotes that are going to be like this. And it's going to be roughly at x is equal to minus 1, minus 2, and x is equal to 2. And so in the middle, you're going to have either that or that. So and on the outside, forget it. There's no max or min. So if we have this, there's no real max or min. There is a slope there. That's not real max. If we have this, we do indeed have a max. So our first step would be taking the derivative of this using the quotient function, which will take us sort of a while. It ends up being x squared minus 4 minus x times 2x minus 2x squared, I believe. And when we resolve it, we are going to discover that it's minus x squared minus 4 at the top, and the bottom doesn't matter. When we set that to 0, we're going to discover minus x squared is equal to plus 4. We're going to divide by negative 1, and we're going to say x squared is equal to negative 4. And we're going to discover, no, that's not possible, right? Now, I might have gone fast. I might be wrong, but my point is this probably does that, and it's why there's no max. Let's keep going. Let's just go over to this one. What about this one? Look at the top. Look at the bottom. Study your graphs. You can save hours of anguish by having actually done your functions. So notice this. We have a domain. It goes from minus 2 to plus 3. What happens when this is minus 3? Well, it doesn't matter. So we're not even concerned about it. But over at minus 3, there is this going on. What about this? x squared minus 1, when is that going to be in the negative zone? Well, that's normally a parabola like that, and the whole thing's lowered by 1. So we have this weird dipping here. Now, the problem is that's just the top graph. When we look at this, this is slightly bigger than this. So I know that this is only one term bigger than this. I know I'm going to have an oblique asymptote. And to solve it, I'd have to do a long division and get the equation of the graph. But I'm not going to do it right now. My point is I have to have some idea of what's going on in this graph. And since I'm only concerned about minus 2, the asymptote is over here. So something could be going on. But in this range, we're going to discover, okay, let's take a value of minus 2. Minus 2 squared is 4. Minus 1, so we get 3. And minus 2 times here, so we get minus 1. So right away at minus 2, I should sort of figure out what's going on. Now I'm going to take 3. 3 squared minus 1, 8. 3 plus this, 6. So we get the value 4 over 3. 4 over 3. So there's a good chance that there is no maximum going on in that range. To understand it further, you have to find out more things about it. But I believe you're just going to have a curve that goes on like that and tries to hug the oblique asymptote. And so within that domain, rather, you're not going to have anything. What a waste of time going over that. State the absolute maximum and absolute min each. Okay, so notice that they have endpoints on some of them, and some they don't. Okay. So they have endpoints on some, and some they don't. So this has an endpoint, and this has an endpoint. Is this lower than that? No. Is this higher than that? No. So these are definitely the max points. So let's find the max points. Minus 2, comma 8, and 3, comma minus 12. Boom and boom. Great. What about this one? This one has an endpoint here. Is it lower than the min? Yes, it is. So that's the min point. Minus 6, comma minus 5, it looks like. Minus 5. What about this? Is this higher than this one? Yes, it is. So this is the max point. Minus 2, comma 30, whatever it is. These have finite points. Notice there's only a max on this one. The min is over here. So that's the max, find the point. That's the min, find the point. What about this one? Finite ends. The min is on this min is lower than that left. So that's the min, and that's the max. Determine the absolute extreme of each function given the intervals. Now, given the intervals is the key there. You must calculate the intervals as well. So what you do is you just take the derivative of each one of them. Okay? Some of them are going to take longer. Some are not. This one's pretty clear. I don't even think you need me for this one. Okay? Keep in mind your domain. Derivative is 2x minus 4. Let's set that to 0. There's only going to be one position here. It's going to be x is equal to 4 over 2 or 2. Let's plug that in. 2 squared 4 minus 8 minus 4 plus 3 minus 1. So we're talking about the point 2 minus 1. So the question is that point lower or higher than the endpoints? Okay? So we need to know the endpoints. Let's plug 0 in. It's quicker. We get 0, comma 3. That is higher. See the y value? That's higher than that one. Let's plug the 3 in. We get 9 minus 12, which is minus 3 plus 3, 0. So we get 3, comma 0. So what we're talking about is point 0, comma 3. Then it dips down to here and comes back up to 3, comma 0. That is indeed the min. There's the min. Where's the max? That one. So the max is 0, comma 3, 2, comma minus 1. You might say, how do I know there's not like a super wiggle somewhere in there? Because I know this graph. And actually I even drew it wrong. It goes like that. And guess what? That's the vertex. That's 2, comma minus 1. And I should have immediately said, well, if that's the min, that's the vertex. And I don't even have to look at the endpoints, because that's the vertex every time. The first derivative of a parabola is always going to be set to 0, is always going to be the vertex. What about this one? That's also parabola. I can just use some logic for that one, right? I don't even need to analyze it. What's the logic of that? Well, it would have helped to study my graphs. I'm going to immediately know the y-intercepts for this happen to be at 2 and minus 2, plus 2 and minus 2. And since this is an upward-facing parabola, I know my intercept's going to be right here at 0x. So I'm just going to set x to 0, minus 2 squared, so 0, comma 4. So I'm going to set it, try it again, 0, comma 4. So right away, yeah, so the other thing is, it doesn't cross, it doesn't cross the intercept. I made a mistake on that. Because of this is the point it double dips on the intercept. My bad, quick misreading. I was thinking of x plus 2, x minus 2. But that tells me it dips here, double dips, which means that's going to be the vertex right there. And right away, I should have said, yeah, the vertex is 2, 0 from my knowledge of the vertex format, x minus h plus k. So 2, 0 is the vertex, which means that's going to be the min point right there. I don't have to take the derivative. The vertex of a parabola is always going to be a min. My brain just doesn't work these days. This is a cubic, so I got a different situation. If there was ways to identify things right away, I should, but I also have to remember I have a domain issue. It's an unusual cubic. I could factor out x squared right away and realize x minus 3 is in there. So that means if I'm going to draw that, I know that at 0, it does a turnaround because it's squared. And then I know it comes down somewhere. And then I know it comes through the graph right here at 3, 0. So I know a lot about it right now. And I also know that is an endpoint. I know it goes off into section 1 and starts down here in section 3. I know it also goes through 0, 0. So I know, since they gave me the domain from minus 1, that's my only concern is if this endpoint here, because it doesn't go off forever, stops at those endpoints. My only concern is if this endpoint is lower than that point. This is going to be tied with the maximum. So you might say, oh, what do you do when it's a tie? That's a good question. You'd say they both share the maximum value. And you should also plug in 3 and realize, yeah, it comes to 0. And plug in 0 and make sure it comes to 0, just to be sure. But here we want to take the derivative. So I'm going to take the derivative of this up there. I get 3x squared minus 6x. I'm going to factor out an x. I get 3x. Actually, I'm going to factor out 3x. I get x minus 2. And I realize there's two derivatives. Like I said, there's this one where it does that turnaround. And there's this one at 2. So at 2, when I put that in, I get 8 minus 12. And that's minus 4. So at 2 minus 4, I've found my min. There's my min. And there's 2 max. Good question whether you would state them both as maxes. And I forget the ruling on that. Ask your prof. That's a cubic. It's a pretty normal cubic. The question is whether it's max or min. It's bigger or lower than that. And that's the trick to these. Okay. So take the first derivative. You get 3x squared minus 6x minus 12. Factor out 3. You get x squared minus 2x minus 4. And I want you to always pause the video when I've taken you far enough and you can solve it yourself. So what multiplies gets minus 4 and adds up to minus 2. Plus and minus 2 doesn't work. Just make sure I did my factoring right. Minus 2. And make sure I did this right. 3 times 2. Nope, you see that? Look at that. That's what happens when you're tired. That is 6x squared. Yeah, no, I think I did that. 12. Yeah, no, I had this wrong. So when I factor out 6x squared, sorry, when I factor out 6, I get x squared minus x minus 2. That makes a lot more sense. So it's x minus 2, x plus 2, plus 1 rather. So I now know that I have two maximums and a max and a min on this curve. And it's at 2 comma something and negative 1 comma something. And I also know that I've got a limit on my upper end. This is not in my domain. So that means I have to get rid of it. Doesn't count. So I'm only looking at the minus 1. And when I put minus 1 in here, I get minus 2, minus 3, plus 12, plus 1, 13, minus 5, I get 8. So that's a max, and my only concern is if it's higher than the endpoint. Now, if you were to take the second derivative, let's just take the second derivative of this one, and 12x minus 6, you can now plug this minus 1 in there, and this is jumping ahead on the chapters. And if it's minus, so minus 12, minus 6, it is minus, we know we've got a concave down. That's what the second derivative will tell me. If I plug this into the second derivative and it comes out minus, I know I have a concave down. So that means I'm dealing with a max point. And just the question is, when 0 is in here, I get 1. So 0 comma 1 is lower. And when minus 2 is in here, I just have to make sure that's lower. Well, I can tell you it's going to be lower. So minus 2 is minus 16, minus 12, plus 12, so they cancel out, plus 1, but I'm way down here. So that's my max, and that's my min. So the left value here is going to be my min, and my derivative that came out to x minus 1, this minus 1 here, minus 1 comma whatever, that's my max. Oof. There we go. Now this last one. And you can see it's just a lot of legwork. Great. So my first derivative, f prime, it's going to be x squared minus 5x plus 6. And I've got a finite beginning and a finite end. This is a cubic, and it's upward facing. So it's going to have a max and a min. If I solve this, I get x minus, what do we get? Minus 2, x minus 3. So the max is going to be at 2 comma something and 3 comma something. And do those fit within? Yeah. So let's figure out when it's 0. When it's 0, it starts at origin. If I take my second derivative here, I get 2x minus 5. I can plug in my 2. It's a negative, so I can tell you that's going to be the concave up. And this is going to be the concave down, which makes sense because this first one has to be the concave up. So now I can just plug 2 in, and I get a third of 8. So 8 over 3 minus 4, 2 minus 10 plus 12. And I'm going to discover it's roughly plus 2. That's roughly 2. So it's roughly 4 and 2/3, something like that. When I plug in 3, I get a third of 27, which is 9. And I get 9 times 45 divided by 2 minus 22 or so. And then I get plus 18. So I get roughly minus 4, around 5, 3 comma 5. And then it goes back up. And actually it's going to be lower than that because I already determined that this is 4.3. So if I put my 3 value into my second derivative, I get plus 1, which means, yeah, it's a concave up. And it's got to be lower than the max. You can't do a turning point and somehow end up above it. So I did the calculation here wrong or here wrong. But you should punch it in to get the exact coordinates. And the question is, what happens when it's 4? Is it higher? So 4 to the third is going to be like 64, and the third of that is going to be, like 21. And then it's going to be minus 16 times divided by 2, 8 minus 40. And it's going to be plus 24. It's going to be about 45 minus 40. It's going to be about 5. So your big concern is whether this endpoint, 4 comma 5, is bigger than this. If it is, that's the max. And guess what? That's the min, because that's below that. Make sure of your calculations. You got to punch in to figure out if these are. So in this case, the endpoints are the thing. Using the algorithm, find max and min values, determine the absolute extreme values of each function given the interval. It's the same thing, it's just tougher derivatives, right? So I'm not going to do all these. And that's because this is the basic stuff. What I'm going to do instead is tell you what you do. So find the coordinates of the start point. It's 1 comma 5. Find the coordinates of the end point. It's 10 comma, let's see, it's going to be 10 plus 2/5. 10 and 2/5. Find the first derivative. It's going to be 1, and then it's going to be minus 4 over x squared. If you can't do that, go ahead and plug it in. Set that equal to 0. Okay, so that would be negative 4 x squared is equal to negative 1. So that would be negative x squared. How am I going to get this up? I'm going to multiply both sides by x squared. I'm going to get negative x squared is equal to negative 4. I'm going to be x squared is equal to 4. When I take square root of both sides, it means x is minus 2. And x is positive 2. So that means I have my two local max and mins. I just have to plug it in to see if it's lower than that and higher than that or whatever. And if my y values are lower, then I found my min, and if my y values are higher, I found my max. So for the 2 is simply 2 plus 2, 2 comma 4. And for the other one, it's minus 2 minus 2. So it's minus 4. So neither of these are higher or lower, right? The minus 4 is lower than both. So this is my min, and this is my max. It's the same thing over and over again. You just got to get good at the derivative part of it. Okay, so what about this one? Same thing. Find the solution, find the point, the beginning point, 2 comma something. Find the end point, 9 comma something. So 2, it's going to be, it's going to be 4 square root of 2. And 9, it's going to be 12 minus 9, 3. And actually, no, I got this wrong. It's not 4 square root of 2. It's 4 square root of 2 minus 2. So, 4 times 1.444 minus 2. It's roughly 3.5 something. And then for the 9, it's 12 minus 9, which is 3. And then you take the derivative. So remember how to rephrase it. The derivative of this is 3 over 2 over x square root of x, because this becomes minus a half, and then it goes down the bottom, minus 1. Then you set this to equal to 0. So you got to bring this up, obviously. Well, let's first get that 1 on the other side. And, there's 2 methods to do that, by the way, and I'll show you both. So now we got to get the x up. So multiply both sides by 2 square root of x. So you get cancellation here. You get 2 square root of x is equal to 3. You now have to solve for 2. Divide both sides by 2. You get square root of x is equal to 3 over 2. And to solve this, you must square both sides. So you get x is equal to 9 over 2. Now, I hope I did that correctly. I think I did. And then you must plug x 9 over 2 into it. Notice there's only one value, and that's because this graph is unusual. So if I was to rephrase this graph and put it all over the same denominator, I would get x squared plus 4 over x. So I have an asymptote there. And I have an upper thing that's always positive. So this is always positive. So it's going to do this weird wiggle through origin most likely. And at origin it's going to have the asymptote. So it's going to be doing this weird thing. But there is a max point somewhere on this. And you just need to see if that max point, when you plug it in, is going to be higher or lower than either of these. If it's lower, you got a min point, which is this. If it's higher than the y values of this, you got a max point. Otherwise, one of these is the max and the min. Same thing over and over again. It helps if you discern your graphs. Now, I said before that I was going to show you a different method here at this stage instead of getting x all alone, and I will right now. Because you've learned over and over again for the other ones when the numerator is set to, let me make sure I got the derivative correctly. So I'm going to get 2, I might have had the derivative incorrect actually. So I'm going to get, was this the equation we were working with? Yeah, it was. I might have had the derivative incorrect. I'm going to get 2 over square root of x. Yeah, I had the derivative incorrect, sorry. Is equal to 0. That's not, I don't know where I got that. Somehow I put in the wrong thing. So this is actually something you got to solve. And again, you're going to discover square root of x is equal to 2. Sorry, my bad. Therefore, x is equal to 4. So you're going to plug that in to figure out where that is. 4, it's 5, 4 comma 5, and then you just got to see if that's above or below the other one. But I want to go back. And I want to go back to this stage. You can also express this as something all over the square root of x, and that would be multiplying this by square root of x over square root of x, and you get 2 minus square root of x all over square root of x is equal to 0. You can now just ignore that and solve for the top. It's the same thing. And that's why when you're finding it, when it's all over one thing, you can just set the numerator to equal to 0. And that's why also you can solve it, but you're going to end up with the same answer. This can be very confusing to do, but I wouldn't mind doing it in the beginning of any graph to express it differently. I just forgot that I'd taken the derivative, and I think I took the derivative twice, which is what happened to me. What about this one? Well, don't forget the domain. It's 0 to 2, so we don't care about anything about 0 or 2. So set the domain for 0. When this is 0, the whole thing is 1 over 2. And when this is 2, 4 minus 4 plus 2, it's 1 over 2. This is a parabola, and it's 1 over a parabola. So that means as the parabola gets big, the y is actually going to get small. And when the parabola gets small, the result is going to get big. So you're actually going to look at something like hug, 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 something weird like that, I think. And there's no value of x down here. Let's see if there is. X plus minus 2 minus 1. No. There might be a value of x that has an asymptote, but I don't think so. I don't think there's any value of x that creates a 0 down here. Anyway, you found the endpoints. Let's take the derivative. To find the derivative, this is not the quotient function. This is the same as that to the negative 1. And now you have to do the chain function. So you end up with x squared minus 1 minus 2x plus 2. All of it times the derivative of the interior, 2x minus 2. Right there you have a formula that's good enough if we had x values. But we're going to expand it. Now, the only problem is we're not going to expand it. Sorry, I forgot the minus 2 over here. This equates to minus 1 over 2x minus 2 all over this thing down here. All over this squared. Now this is an example where if you set this to 0, only the numerator matters. So the minus 1 doesn't even matter. So the question is, when does this become 0? Well, obviously when 2x is equal to 2, when x is equal to 1. Okay? So that means you plug 1 back into here and you discover somewhere between these 2 points, I get 1 over 2. And look at that. It's the same y value. Oh, I don't get 1 over 2. I get 1 minus 2 plus 2. So I get 1 over 1. I get 1 over 1. 1 comma 1. That's clearly higher than this and higher than that. So you're going to get this weird little bump over here. And sure enough, if we just plug this into Desmos, it's always good to understand your graphs, right, by the way. Y is equal to 1 all divided by x squared. Was it plus 2x or minus 2x? Yeah, that's good enough. Let's see. Yeah. There we go. And keep in mind we're working with this range. 0 smaller or equal to x, smaller or equal to a 2. So, did I screw that up? Oh yeah, I did. A is equal to 2. There we go. See? And that's what we discovered right there. And this is the whole graph. This is what happens when you take 1 and divide it by a parabola. The extremes are tiny, and you got a big bump here wherever the parabola was coming close. And guess what? It's going to share that as the vertex of the parabola. So if I do another line here, and just put the parabola in, oh, look at that. Okay, notice as the parabola goes up and we take 1 and divide it by a bigger and bigger number, we get smaller and smaller on our graph. Same with this side, and it's only at the vertex that we will get a bump, and we're only going to rise as high as the vertex. In this particular case, in this particular graph. Always helps to understand them. So let's keep going. These will, stuff like this will definitely be on section 3. And just keep understanding your graphs and keep understanding your extremes. Okay, what kind of graph is this? It's a cubic. Solve for the endpoints, right? Solve for the endpoints. Take the first derivative. I'm going to just make it a little bit larger for you. So polynomials are just so easy to solve. Okay. You're going to discover that you can probably take a something out of this. Yeah, you are 72x, because they're not going to give you one that's too hard to solve. So that's the derivative. We set it to 0. I discover that I can take probably 4x out of each thing. So 4x, left with x squared minus 3x. And what is that? 36 minus 18. Does that make sense? They're all minus for sure, except for the first one. So I just have to set. So now I realize, oh, when x is 0, I have an extreme, and that's within my domain. And then I have to solve this. So I get x, I believe it's plus 6 minus, it's x minus 6, x plus 3. So now I have 2 more when x is equal to 6, and when x is equal to minus 3. And that makes sense because a quartic, remember, a quartic is going to start up here. It's going to have this. So one of these is that little W bump. 2 of these, and I can tell you right now, this one's going to be the W bump because it's in between the x values of these, and you can't have a W that doesn't have that in between the 2 bumps, right? So this is going to be the top part. This is going to be one of the bottoms on the right. This is going to be the other bottom on the left. And just the question is it higher or lower than that? So you should solve for this. For minus 3, find the y value. Solve for 4, find the y value. This is where Desmos is really good. So to confirm answers anyway, because if I have y is equal to 3, x to the 4 minus, I'm going to get rid of that so I can just lower stuff. There we go. Minus 12x squared minus 72x. Oh, I didn't write in the actual thing. I'm trying to write it in the actual one. Minus 4x cubed minus 30x 6x squared You might say, well, this is a waste of time. No, you're going to understand a lot more when you graph things. Get rid of this thing. Doesn't matter anymore. There's my crazy W. I can even put in my domain limitations, -3 and 4. Okay, boom. Notice I've got some issues here. So this is not going to be my min. My min's going to be this one. So there's the 3 that we solved. And this is not going to be my max. There's the W we solved, the top of the bump. This is going to be my max. So all you're going to do is you're going to change this to f of x because it lets you solve things. You can also take the first derivative like this. You can make h of x equal to f prime. And now you have a nice derivative equation, and you can even set 0 to equal to h of x, and it will tell you, turn off everything else, it'll tell you the 3 max mins. And let's see. Yeah, so it's at 0, 2, and 3. -2, 0, and 3, like we solved. And so that's nice. You can also show the graph of the derivative, which we know is going to be a cubic if you needed to. But you can also solve for the extremes. So here's -3, right? I can just say, what's f -3? 47, great. What's f4? Great. Now I can solve for my other ones. What's f -2? Great. What's f 0? Great. What's f3? Great. So I discover right away my f3 is the lowest point, and I just have to find my biggest y value. Now it is right there, f -3. So I've discovered that my start point is my max, and my right side of my w minimum is my lowest point. Makes it a lot easier than, and you might say, well, on a test I'm not going to have that. Well, you're allowed. Your graphing calculator can solve it the same way. You're allowed to use a graphing calculator, but suppose you don't have one. Yeah, you have to do a lot of hand calculations, and he's not going to give you something that's impossible to solve on a test. If he is, you have a professor that's kind of, I don't know, he's not trying to teach you, he's trying to stump you. Avoid those professors. Oh, okay. So it has a min, it has a max. Is there any value down here that can create a 0? No, because of that. There's no way to create a 0 because of that. So we're going to have this weird bump thing, or we might have, if this is the graph, we might have this weird thing. Because this is always going to be positive, but this can be negative. And so at this part, suddenly the graph's going to go into negative y values, and to the right it's going to be positive. So we're going to have something like this. However, I happen to know that these things tend, just like that other drawing we did, they tend to hug, create a bump, go through, create a bump, and then hug again. They're going to go through right 0, 0. You'll need to figure out this point. So you plug it in, -8 over 5 is the y value. You need to figure out this point, which is 16 over 17. And then you just need to figure out these max and mins. So we use a quotient rule for this. The quotient rule says that 4 times this minus, all in brackets, 2x times 4, so minus 8x, 4x squared minus 8x plus 1, all of it over that squared. But when I set to 0, this doesn't matter. I'm just concerned about the numerator. If you don't understand why you only have to set the numerator to 0, okay? I want you to look at this. What do I have to plug in for x to make this numerator, to make this whole thing fraction 0? Well, obviously 5, right? What role did that 5 play? None. I just had to set this top. And that's because as long as this comes out as a number, in other words, as long as this x value doesn't create an asymptote down here, the denominator doesn't matter. denominator doesn't matter. Just as in this case, the denominator doesn't matter. We just have to solve for this to figure our max and mins. Okay, so we need a number that multiplies out to 4 and adds up to minus 8. And so at this stage, I always want to make sure I did it correctly. 4x squared plus 4 minus 8x. 2 minus, yep. And I'm ended up with 4x squared. So I'm going to suggest to you that this does not have a max min, because I do not believe there's anything. However, you should always take your quadratic function. Unfortunately, I grabbed an Excel sheet and just made my own quadratic function out of it. It's always nice to have your own quadratic function calculator. However, Desmos will also do it for you. And I'm going to set my thing at 4 minus 8 and 1, ABC. 4 minus 8 and 1. It's going to tell me here's my discriminant, and I'm going to discover some values for x. So it's x minus 1.866 and x minus 0.33. So I'm going to just take a screenshot of that. I'm going to go back to my graph. So there were solutions to it. And it means the solutions for this are when x is equal to 1.87 and when x is equal to 0.3, and you would plug it in. So I'm not going to do that. I'm going to instead set my Desmos up here to equal to my thing. You might say, well, I don't have enough time for this. Yeah, that's right. But the time you do spend analyzing these things is less stress on a test. And that's what nobody ever gets. You mortgage your time, you cram, and then you flunk the test. Well, all you're doing, so my calculations were totally incorrect. So that means I did something incorrect when I took the derivative, right? But the bump, and I should have said, remember my drawing. There has to be a bump there because I know what this graph looks like. It looks very much like I said it would, doesn't it? So right away I should have said to myself, you did a derivative incorrectly there. So you're going to go back. Notice they changed the conditions here. They give you the same graph but a different domain. You're going to go back and you're going to do the quotient rule. The quotient rule says you're going to make f of x equal to 4x, which means f prime is 4. And you're going to take g of x is equal to x squared plus 1, which means g prime is 2x. And then you're going to put it into the thing, 4 times x squared, into the quotient rule. This is the quotient rule, f prime times g minus g prime. No, still so far so good. All over this squared, but I don't really care about that. I only care about the top. So I still get 4x squared, and that's the problem right there. Plus 4 minus 8x squared. So I did not do my g of x correctly. And actually it's not 8x squared. Yeah, so that's just 4x, so I also wrote that. It's 8x squared. So I actually have minus 8x squared. Sorry, minus 4x squared plus 4, which is much easier to solve. So I take a minus 4 out of it. I get x squared plus 1. Now I just have to solve for that. Nope, I still did something wrong. Yeah, when I take minus 4 out, it's x minus 1. So when x squared is equal to 1, so x is equal to plus 1 and minus 1. So I did my calculations. See, that's what happens when you rush. Totally incorrectly. And sure enough, it's 1 minus 1, and I discovered that those are the max and mins compared to the beginning. What did they do in the second part of this question? They changed the domain. So one domain is from this. Right? And one domain is this. They made it smaller. So right away, you're going to discover once they get rid of that maximum, you pretty much have to calculate this part and this part to find the max min, so the beginning point and the end point. And it helps to know from the question before that the max points and min points are excluded in the second question. So you're just talking about this part of the graph, which the end points are the only max min. And they're trying to train you how to analyze data properly. That's the whole point of this. You're going to discover a lot of these things in biology or chemistry, where you have data that matters and data that doesn't. Then they get into word puzzles. An object moves in a straight line, its velocity. So its velocity, it's time. So they give you a velocity based on time. Determine the max and min velocities in this time interval. Same thing. Then they change the time interval for the second graph. Oh, they also changed the exponent. So that means you have to find the derivative of this using the quotient rule. That's your f of x. That's your g of x. This is your derivative of f of x. This is your derivative of g. And then you plug it in. And I'm going to ignore the denominator of the derivative for now. And so I get 4t squared times, I might as well use my stuff. I use 8t times this, put it in brackets, minus big old brackets, the derivative of this, which is 3t squared, times this. What's 3t squared times 4t squared? 12t to the 4. Eight t, you get 8 times 4 is 32t plus 8t to the 4. So you get 8t to the 4. I hope I did this right. 8 to the 4. 8t to the 4 minus 12t to the 4 is simply minus 4t to the 4. So that's your derivative. It's all over this thing squared, but when we're solving for 0, I'm only concerned about the top. I can factor out a t, and a minus t actually, and I'm left with, I can actually factor out minus 4t, and I'm left with t to the cubed minus 16, 8. So notice that t0 is one of them. It makes sense because this is a cubic. The derivative is a cubic. And when I solve this, I discover that t cubed is equal to 8, therefore t is 2. So if t is equal to 0 and t is equal to 2, I'm going to get, and this is going to be a triple wiggle here, I think, or a double wiggle, I'm going to get a max and a min. And the first question is, they gave me bigger or equal to 0, so that's in, and that's in. So first I have to solve for 0. So when I solve for 0, I get 0 over 4, which is 0. So it starts at origin. And when I plug in for 2, I get 16 over 4 plus 8, 12, which is 8 over 6, which is 4 over 3. So 4 over 3. So my only other concern is, what's a max and what's a min? Sorry, so the points 0, 0, I know is the beginning point. Then 2, 8 over 3 is another point. I just have to figure out is this second point, or what happens when t approaches beyond this point, like 10. You just use 10 if you want, or use a number that works well in here. Actually, 10 works great. So top, you get 400, and bottom, you get 10 cubed is 1,000, 1,004. So what is it approaching? As x gets bigger and bigger, it's approaching 0. So we're getting a thing that's hugging the y. Is that bigger than 0? Yeah. Is that smaller than approaching 0? Yeah. So that's a min, and that's a max. Because this graph is going to look like this. in this domain anyway. Zero, zero, up to about 2, 8 over 3, which is roughly 2 and 2/3. And then it's going to dip and hug. It's never going to reach the y-axis. It never can. That can never reach the y-axis because this is always positive, and this is always positive. And if we were to go through, we're going to see a repeat on the left side of the same thing, because both of these are all... Actually, no, this can be negative. So on this side, we're going to see a cross through and a reflection. So graph it. 4t squared over 4 plus t cubed. 4x squared. By the way, it's easier to do x's. And was it 4 plus? 4 plus x to the cube? We'll find out in a second. 4 plus x to the cube, 4t squared up top. And we're going to set it 0 to infinity. And sure enough, there's our, I got the, it wasn't 2/3, I got the 8/3 wrong. So it must have been 5/3. So I did a small calculation error, so make sure you don't do calculation errors. And then sure enough, it hugs. Now if I get rid of that domain, ooh, oh, of course, yeah, because this does have an asymptote. So if that didn't have an asymptote, it would indeed reflect here, but I sure realized it has an asymptote. My bad. And good example of not realizing that there'd be an asymptote. If there wasn't there, you would indeed have a reflection kind of graph situation. So I don't know if I can do it with it to the 4. Yeah, sort of. Doesn't quite do it. Let's put a negative in front of this whole thing. No. An absolute. Absolute won't do it. Let's do absolute up here. See what I get. If I can create it. No, because that's always going to... Oh, and then I'll just make it... No, that won't work either. Oh well. Doesn't matter. I'm just screwing around. So make sure you do the calculation right. Now, what changes with this one? Don't forget they make it squared. Okay, so let's go back to what we had. This time they make it squared. And they changed the domain, I believe. No, it's still the same domain. Let's get rid of the domain and realize that this time the bottom can never have a positive, a negative, and the top can never have a negative. So it's going to reflect perfectly. So we're going to take the same process and this time we're dealing with this 1 plus t squared instead. Okay, so f of x is equal to 4t squared, which means f prime is 8t. G of x is 1 plus t squared, which means g prime is 2t. So I get 8t times g prime, 1 plus t squared over here, minus f times g prime, so that's going to be 2t times 4t squared, which is minus 8t cubed again. Oh, squared. 2t, that's 2t times 4t minus 8 cubed. So I'm going to get 8t cubed here minus 8t cubed. I just want to make sure I got that right. I did. They're going to cancel out, and I'm going to just be left with 8 up top. 8 up top. Huh. So I got 8 up top over this thing. So that leads me to believe I want to do my derivatives just to make sure. 8t times 1 plus t squared is going to go up to 8t plus 8t cubed. And then minus 2t times that is going to be 8t cubed. So these are going to cancel out. Oh, I forgot my t. How stupid. So I got 8t is equal to 0, which means there's only one value where it has a max. Let's see if that is true. No, that is not true. Oh, yes it is. Look, it's always rising. So the 8t is a min, okay? And it never approaches. And right away, you can say, oh, wait a minute, I should have just realized that this is that, and that these cancel out. Okay, they don't cancel out, but that if I look at them and rearrange them, I realize that they're the same terms, so there's going to be a horizontal asymptote at y is equal to 4, and it's probably going to always try to rise to it. Okay. Set y is equal to 4. Yeah. So it helps to know your graphs. So it'll have a min, but there's no real max. I mean, it approaches 4 on the other end, but never gets there. So at the extreme value to the far positive infinity, it approaches 4. That was a long one for no good reason. So also feel free on these things to always fast forward me, because I go on and on and on and on and on, and I know it. Okay, let's go to the next one. A swimming pool is treated periodically to control growth of bacteria. Notice when we're measuring times, we're only concerned to the right of origin. The number of bacteria is equal to number of bacteria based on time, which is in days. Determine the lowest number of bacteria during the first week. So there's a maximum. So first thing we should do, and they gave us a limit. First week is the first 7 days. So they're saying from 0 to 7 days is our domain. First thing we should do is calculate 0. At 0, we have 500 bacteria. Next thing we should do is calculate 7. So it's going to be 30 times 49 minus 7 times 2 times 740 is roughly minus 1750 plus 7. I think it's 1680. Let's find out. Yeah, minus 1680 and plus 500. What's this one? Well, 10 times 40, 490. 3 times 500 would normally be 1500, but then we have to subtract 30, so we're talking 1470. 1470 minus 1660 is the same as minus 1, 2, 10, plus 50 is minus 2, minus 160. Now, you want to go back and do your calculations and make sure that's true, but this is definitely close to 1500. This is definitely more than 1500. Ah, there we go, plus 500. So I got minus 210 plus 500, so that makes sense. So plus 290. So the end point of this bacteria is 0, 290. So notice it starts bigger than it ends. Take the first derivative, 60t minus 240, set it to 0, 60t is equal to 240, t is 6. So on day 6, we hit a max or a min. Now guess what? I can take the second derivative, and I'm left with 60, and that's a positive number, so I know we're dealing with dealing with a min. Does it go down at first? And the second derivative doesn't, it doesn't matter. Let's just plug 6 in. So it's going to be 30 times 6 squared, so 30 times 36, minus 240 times 6. So what's 6 times 250? It's 1500. And so it's going to be 1440. We just got to figure this one out. All plus 500. So let's just do the 500 here. So we get minus 940. So what's 10 times 360? Or 36? 360. What's 3 times that? 180 plus, it's 1080. What's 940? 1080 minus 940. We're talking about a small amount. It is 140. So it starts big, dips down to 140, so it is a min, and then goes back up to 290. So it starts here, on the x-axis, dips down, and then goes up. So we're talking about a min. Determine the lowest number. Well, the lowest number is 100 and, where did I put it? 140 on day 6, 140 bacteria. So here's the graph. And you might say, where is it? And good question. 3x squared plus, oh, it's way up at 500. So, Jesus. I don't know if it'll take me there. I don't think it will. So we're going to look way up here. We're going to start it at 500 to 600. There we go. It's going to take us there. And just remember that x is bigger than 0. X is bigger or equal to 0. So, sure enough, there's a graph. We should also set the limit. 7 is bigger or equal. So there it is. There's the graph. And sure enough, I got my numbers wrong. I got everything wrong. How did I get everything wrong? Wow, good thing I'm checking. 30x squared minus 240x plus 500. Wow. Oh. And here's where your basic math fails. That's not 6, that's 4. Now I have to plug 4 in to figure out what it is. So it's 30 times 16 minus 4 times this is like 1,000 minus 40 plus 500, so it's minus 460. This, 160, is indeed 480 minus 460. So the lowest is 20. And you can see my basic math skills failed me miserably. However, the concept is correct. Take the derivative, set it to 0, figure out the min, determine if the min's below or above the endpoints. So there we go. And sure enough, there's the max after 7 days, and it starts off with more bacteria. So the bacteria is growing in this graph. Stupid me. So good thing I have Desmos so that you don't scream at your screen, you're an idiot. Which, you know what? I actually find the more you do this, the more mistakes you make. Not when you're learning, but when you think you know it all already, because you're just not being careful. Ask yourself, will this graph ever be negative? What does V measure? So clearly this is an efficiency measurement based on speed, velocity. So speed goes in here. What happens to this graph? So ask yourself what happens at 0. When speed is 0, the graph is 0. This will never produce a negative number. This will, but we're only concerned about 0 to 100, which will never produce a negative number, which means our graph goes up. However, notice right away in the initial values of, let's say, 1, we're talking at 1, it's going to be 1600 over 6400. And then as V goes up, this is going to dramatically climb, but this is going to make things okay at first. So what we're going to see is it's going to climb and then stable off, because as V gets to 100, so let's take it for 100. Let's ignore the, 1600. So when V, let's take the max, and down below we're going to get 1000 plus 6400. So we're going to get 16,400. So you're going to notice that even when V squared, it's not keeping up with this number. And so as V gets huge, yeah, it's going to exceed this number. So, but we're going to see a rise and then a fall. So we're going to see a maximum, especially since we start at 0, 0 efficiency. It's going to be a max somewhere, and that's going to be fall. So normally I would say figure out 0, 0, and 100. I'm going to let Desmos do that. But before I go to run Desmos, let's figure out the max. Okay. based on the derivative. So clearly on this, we're going to have to take the derivative based on quotient. Quotient rule says I'm going to have f prime times my g of x minus big bracket my g prime times my f of x. And it's all going to be over that thing here squared. But when I set to 0, I don't care about the denominator. So I'm going to have 1600 v squared here plus minus 2 times 1600 v squared minus 3200 v squared. So this is essentially just going to become minus. So you set it to 0. This goes to the other side of the equation, becomes a negative. So you just have to take that number we got and divide it by 16,000 essentially. And just make sure 1600, yeah. So you get 6400, but remember it's v squared is equal to that. So now you got v squared is equal to that. So you're going to take the square root. You're going to obviously see that it's going to be like 80. 80. So that means we're going to hit a peak when velocity is 80 kilometers an hour. And how do I know it's a peak? Because I know already that this graph goes up and then starts to dive. When v gets huge numbers, it starts to dive. But in the beginning, this number is enough to defeat that. So it's going to rise to 80 and then it's going to start to decline. So if the speed is 100, determine the legal speed that will maximize fuel efficient 80 kilometers. The legal speed that will maximize the fuel efficiency is 80 kilometers per hour. Never forget your units. You'll lose marks. Repeat part A using speed limit of 50. So speed limit of 50 tells me that because it's on the way to the max here, that 50 is going to be the max. So the answer to that is velocity is equal to 50 kilometers an hour for maximum fuel efficiency, because in the beginning it's 0 and it only can climb. There's no turning point. I mean, I suppose I should test more to make sure of that, but all I would do is put 50 into the formula, and I know 0, 0, and I know, I mean, it's not going to do that. It's going to have a climb to the maximum. Determine the speed intervals within the legal speed limit of 0 to 100 in which the fuel efficiency is increasing. Okay, so that's from 0 to its max. So from 0 to 80 kilometers per hour is the interval. Determine the speed intervals within the legal limit in which fuel is decreasing from 0 kilometers an hour to 100, because that's a max. That's a max. How can I make sure it's a max? Well, visually I know I'm sure it's a max. They want me to plug in the numbers over and over again. But you can also do this. No, actually I can't, because I'd have to go back and have the whole second derivative. You can take the second derivative and then plug in the number of 80 to see if it comes out. But I think in this case the smartest part is plug in 80, plug in 100, plug in 0, and then you'll see which point is higher than which. But let's let the computer do it. Is that it? I can't remember. Let's see. 1600 v squared plus 6400. Oh, notice that. I wonder if it'll work with... Yeah, there we go. If you're changing the v's, it's got to be f of v. That's the only thing. Okay, let's put a 0 to 100 here. Did I do it properly? Oh, There we go. Then I'm going to take the first derivative. Set it to 0, or better yet, I guess I have to do this. 0 is equal to the d over dv of f of v. Does that work? No. Do I have to change everything to x? I think I probably have to change everything to x. And then suddenly it lets me, does it suddenly let me do it? 0 is equal to f prime. So that's going to tell me right away that 80 is my max value, that crossbeam. When you set 0 is equal to the first derivative, it will give you a vertical line where that's true. Then I can just punch in f of 80. That's a 10. I can punch in f of 100. That's lower. And I can punch in f of 0. Now you do all those calculations by hand and 0. So I can definitely see that that's a maximum. So that's maximum fuel efficiency. I can see that the interval rises all the way to 80 because it starts at 0, rises to the 80, and then decreases from then on. So we zoom in, and it's too bad I can't just visually show the slope because it's so gradual you can't see it. But here, 80, 10, and look at my y values as I move to the right. It's going down from 10, it's descending, all the way to 100. Watch. Descending, descending. Fuel efficiency is going down. So there you go. You can see visually, it doesn't help us until we start taking derivatives and stuff. This is no different. This one's no different than what we just did. It's just medicine. Again, time only concerns about positive time. And so you take the first derivative, you set it to 0, you'll discover where the max is for, and the minimum concentrations between the first and the 6 hours. So they only care from 1 to 6 hours. So you should calculate your 1 and discover that it's 0.1 over 16. And you should calculate your 6, and you're going to discover that it's 0.6 over 81, and clearly 16. So this is 1 over 160, and this is 6 over 810. If you simplify, we're trying to get something comparable, right? You could multiply this roughly by, if you multiply roughly by 5, yep, you get 5 over 800. And you can see that this is just slightly smaller than that. So that's a good starting point. You can also see there's not much change between 1 and 6. So we're either going to have a bump up or bump down. It all depends what's going on. This is always going to be positive, but we're only concerned about positive numbers, so it's never going to go into a negative. And I believe the minimum is going to either be at the beginning or the end. And keep in mind that this beginning is smaller than the end. So we just have to find the derivative. The derivative is f prime up above times my g of x minus g of x prime, which is just 1. Oh, no it isn't. G of x prime is actually 2 times t plus 3, all in square brackets, times 0.1 t. Ugly, man, ugly. So don't slip up there like I almost did. I believe they want you to resolve it by hand, meanies. On the left, I get t squared plus 6t plus 9, all multiplied by 0.1. Let's just keep that there. On the left, I get 0.2. Yeah. 0.1t. Wow. I get 0.2t times t plus 3. I believe that's correct. But keep it in brackets because this minus will apply to everything in there. See if I can just shrink this part. So this is going to be 0.2t squared plus 0.6. And when I apply the minus, I'm going to get a minus here and a minus there. So I get a 0.1t squared minus this 0.2t squared. So it's going to become minus a 0.1t squared plus 0.6t plus 0.9 minus 0.6, 0.3. So that's what I'm left with. You got to be very careful with your calculations here. You're going to set that equal to 0. Your first step is going to be multiplying everything by 10. Your second step is going to be taking a negative out. Your third step is going to realize that this cannot be solved except with the quadratic equation. And I already feel like I might have made a small error here. But I got 1, minus 6, and minus 3. Okay. And my quadratic equation says that these are the points right here. So I'm talking about a max and a min point. So we're talking about 6.46, but remember my hour limitations? So 6.46 is not included. So we're also talking about negative 0.46. But negative is not included. So that means I might have done a derivative error. Since the max and min seem to be the end point and the start point. I don't believe that's true in this question. So go back to long root. So when you're making errors, and you know you're making errors, you got to go slowly. So I'm going to set my g of x to that. And my f of x to that. And I'm going to set my f prime. And my g prime. Okay, and then I'm going to just expand that to make my life easier. Then I'm going to do the product rule. F and I'm going to replace it. Then I'm going to go slowly and I'm going to expand it. Okay, and then I'm going to apply the minus through it. So far it looks like what I had. Then I'm going to expand this. Then I'm going to expand that. Then I'm going to realize I'm going to be left with, I think I got it right. Oh, did the t's cancel out? Yeah. Alright. The t's cancel out. That's what's going on. So, an arithmetic error. So that's what I failed to do. I hate myself. Plus or minus 3. I don't care about the minus 3. So that's a 3. Now I'm going to plug it back into the original equation to see if it exceeds my max or my min. So I get 0.3 up top. Down below I get 16. And I didn't write down my max or mins, but I believe that's smaller than what we had. I believe I was looking at around 6 over 810 before. So is that a max or a min? So multiply it by 10 rather, and then try to approach this as a denominator, probably by about 5 again. Oh, 15. This is a max. That's above those. So at 3, comma this, the maximum concentration of the medicine is at 3 hours, and then the minimum is at 0. So now we can just use Desmos. I'm making these things a lot harder than I have to be. Okay, and we're going to set the time from 1 to 6. I'm going to go home. And it's nice enough to confirm my derivative is at 3. Okay. So if I turn that off and I look, it's 3.008. If I go back to the beginning, it's less. If I go to the end, it's more than the beginning. So that's the min, and that's the max. And notice visually, it's kind of useless because we can't see curves. So that's when you have to trust your numbers. But I can just right here say, what's my f of 0? What's my f of 3? Because I gotta have, what's my f of 1 rather? And what's my f of 6? It's going to tell me the results, and I'm going to see that my f of 0 is lower, my f of 3 is highest, and that's in between. So that's the min point, and that's the max point. But obviously you want to do it by hand so that you don't make as many mistakes as I'm making. It's going to be the same thing over and over again. My God. I'm not going to sit here and do quotient rule over and over again. It's the same technique. Compare it to your start and beginning points. Okay. Helps if you can sort of decipher the graphs. So what happens here is t gets big, this whole thing gets tiny. At 0, what is it? It's plus 1. So let's start with 0, and oh, look at that. Look at our domain. So let's look at 0. We're talking comma 1, pollutant. Amount of pollutant. Okay, let's look at time 1. So at time 1, you got 2 plus 1 over, 1 over 163. Woo. So there's 2 points we're talking about are 1, comma, and 2, 1 over 163rd. I believe that's correct. Is that correct? Yeah. So just the question is, we know it goes up. Goes up from 1 to that, but does it dip down first, or does it dip up first? Flatline's unlikely. It helps if we understand this equation a bit better. We'll discover that it's actually this. And we'll also discover that it's the same term up top. And it's essentially a parabola divided by a parabola. So it's going to be some sort of line-ish. And it's never going to have a negative number down here. And in the time frame, it's never going to have a negative number down here. And it's just a question of what it does do. So let's take the derivative of the easier one. Rephrase it. This is the same as this, but to the negative one. So the derivative, we can use the simple power rules for most of it. It's going to be 2. And then in brackets, let's solve the derivative of this one. It's going to be minus 1. And then this becomes, it's going to be minus 1 times this to the minus 2 times the internal derivative, which is 162. So we're going to do 2 again plus, and then when I solve this, it becomes minus 162 all over this squared. Great. So now we have the derivative. We're going to set it to 0. Now there's 2 things you can do. You can either move the 2 over here, or you can put it all over the same common denominator. I'm going to move the 2 over to the other side. Get minus 162. Actually, you know what? Yeah, let's do multiple steps. Minus 162. It's the same thing. Here is equal to minus 2. Okay. We're going to multiply this thing by that on both sides. It's reciprocal on both sides. Okay, to get rid of it on the right, keep the minus. Keep track of the minuses. We still got a minus here. Clearly, I want to isolate this whole mess. So kind of do reverse Desmos to unravel equations. And divide both sides by minus 2. This is going to be positive 81. Well, it's starting to make sense now, right? I'm going to take the square root of both sides. I don't care about the plus. I don't care about the minus, just the plus 9. And it's going to be equal to this. So now I've got 162t is equal to 8. T is equal to 8 over 162, which is the same as 4 over 81. And they both can't really be divided by 9. Now I want you to look at this value. This is a 0 value. The question is, does that go above or below? This is a t value. And the question is, does that go above or below? So you're going to get 2 times that. You're going to plug it back into the equation. You get 2 times that. Plus 1 over 162 times that, which just becomes 2, plus 1, which just becomes 1 over 1/3. If we're going to adjust it, I can turn that into that by multiplying by 27. And I get 35 over 81. So the question is 35 over 81 above that and below that? So it's not above that, and it's not above that. It's below that. So that means this whole thing dips down and then rises. And it dips down at the value of x that I plugged in. This is the value of x for over 81 years. So that's rough. I don't know. It's roughly like 2 weeks in. And it dips down to the value of 35 over 81. Desmos is only going to show me decimals for that. 2x plus 1 over 162 2x plus 1. Let's just make sure I got that right. Oh, there's that straight line thing I was talking about. 2 plus 1. 2x plus, yeah, and I'm only going to be concerned from 0, no, from 0 smaller equals x smaller or equal to 1. Yeah, so there's the dip. Okay, so I'm going to see if my values were right. So I said 4 over 81, so I'm going to let Desmos calculate 4 over 81 for me. See if I got it. Yeah, got it. Then I'm going to let Desmos calculate 35 over 81 for me. And see if I got that right. No, I got that one wrong. So I did a calculation error in my y. But fortunately, they didn't ask me about the pollutants. They asked me about what time the pollution was at its lowest level. However, if I if I let f of x solve it for me. 4 over 81. It will indeed spit out that amount, right? So somewhere I made a small calculation error. So I think it was right here when I forgot to multiply that by 2. No, I did. Got 8. And then I got 1 over 4 over 81 times this. Yeah, so I got 8 plus 1 over here, which is 1 over 9. That's where I did wrong. So we're going to multiply by 9 on 9 over 9 here. I get 17 over 81, not 35. Just goes to show that, by hand, yeah, there we go. By hand, you can make so many more mistakes quite easily. Fortunately, I could still answer the question. And this is why it helps to have graphing calculators and tools. Notice how much it dipped and then came back. And that's because this overall graph, as I said, looks like a line that gets interrupted at x because it's a parabola over parabola. It sort of helped me to realize that, right? When I expanded it first and sort of understand this is just a line, but there's a big dipping mechanism going on right near the asymptote. Okay, keep going. So, but it's the same thing over and over again. I don't know if you need me to solve it, so I'm just going to tell you the steps, especially since I'm solving with, like, the point of this is not to give you answers, it's to give you techniques, right? So this is going to be the same thing. You have to compare to the start and the min points to see if it's lower. So I'm going to just go back to my quick ways. So we're looking at a specific domain and how much gasoline it's using in liters per 100 kilometers, where that is measured based on what? The x kilometers per hour. So technically that's velocity in there. Okay? If fuel costs this much, what speed will result in the lowest cost for a trip of 200 kilometers? So that just means what is my lowest rate of consumption in that domain for this equation, which still just means take the derivative, find the max min, compare it to the beginning. So my first step is finding 30. So I get a quarter. 4,900 divided by 30 is the same as 490 divided by 3, but then I got to add 30. So I'd have to figure out what 490 divided by 3 is. Then I have to add 30, and all divided by 4. So I'm going to have to keep in mind that my fuel efficiency in liters per 100 kilometers is 48 liters per 100 kilometers at the beginning. Then I'm going to take it for the same thing, but I'm going to do it for 120, which is the same as 490 divided by 12, plus 120. All divided by 4. Whoops. So careful with that. Make sure you resolve your brackets first. 40.208. So the question is, does my fuel efficiency go up or down? And what will that speed be? So what's the derivative of this? You have two options. You can keep the product up front and take the derivative inside, but if that confuses you, I would distribute your 1/4 x through and take the derivative internally once you distribute it. But let's just remember the quarter out front, okay? What's this equivalent to? So I take the derivative of this, I got to add the derivative of that, and then just remember to multiply through later. So what's the derivative of this? What's the derivative of this? What's 4,900 divided by 4? I think that's it. Yep. So I ended up having to distribute it through anyway. Set it to 0. I could make the whole thing into a, you can do this if you wanted. And that way the whole thing up top becomes, I'll do it both ways, okay? So when you set it to 0, you can solve it like this. Might take you even longer, actually. Multiply both sides by x squared. Multiply this right side by -4. I think I come back to the same thing, right? Take the square root of x. Ignore the -1 that occurs because we're only looking for that. Which means when 70 kilometers, which is in between that domain, it either is a min, I might save amounts, or I might use them. Oh, I was going to show you the other way. So the other way, so let's just put that somewhere. I'm going to memorize it, 70. So the other way of doing it is this. See if I can come back right to the thing. Yeah, okay, I got it right there. You can make the common denominator. Multiply this thing by x squared over x squared. You get this. Oh, you got to multiply this by 4 to get this to the 4. So you get the same thing, minus 4,900. So you get minus 4,900. When you make the common denominator, you get this all over 4x squared. When you set it to 0, this no longer matters. You now just need to solve that. Same answer. Okay, so 70. Now I would just plug that in to see if I get a result that's below this. I'm trying to get below because so far that's the best fuel efficiency. So that goes in 70 plus 70. So I get 140 a quarter. So that's 70.35. So my fuel efficiency is way below that. So this thing starts here, goes down, and at 70, 35 is my best fuel efficiency. you should drive this. I don't know what this has to do with anything. Oh, the lowest fuel cost. What speed? But they're only asking what speed and what is the total cost for the trip. Okay. So then you take 70 is your speed. Oh, and you have to figure out how many liters that's going to cost you. Oh, what a pain. Okay. And 70. All right. So since 70 results in the best fuel efficiency, and the answer to that 70 was, what did it end up being? So it was 70 over that. It was 70 plus 70. It was 140, which was 70, 35. So that was the fuel economy. And it ended up being, you used 35, that was 35 liters per 100 kilometers. He went 200 kilometers, so it cost him 70 liters. And it costs $1.15 a liter. So 70 times $1.15. Okay, I'll go back and do that for you. It cost him $80.50. So what did I do there? I went back to my 70 kilometers an hour that I figured out was the most fuel efficient. I plugged it into this equation, and I ended up getting 70 plus 70 in the middle times a quarter. And when I solved that, I discovered that my best fuel efficiency was the number, my R at 70 was 35. And I had to go back and say, what does Rx measure? It measures how many liters, 35 liters, every time I travel 100 kilometers. Then I went back and said, okay, well, he traveled 200 kilometers right there, which means if it costs you 35 liters to go 100 kilometers, it costs you 70 liters to go 200 kilometers. Then I know it costs $1.15 for each one of those liters, so I multiply $1.15 times the 70. And I get the final cost of $80.50. Let's spit this into a graph. And I prefer doing the graphing to checking the back of your book, because you're going to get a lot better understanding of these graphs and your mistakes and where you make the mistakes than you are just looking at the numbers in the back of the book and seeing an answer. It's just annoying. So x plus x, I think, and it wasn't divided by x. Let's see what it was actually. No, it is. Okay, so let's have a look at this graph and realize that we're going between, what was it, 30, what was our range? 30 and 100 and 120. Okay, and then we've got to find out where this graph is. And when things are 0, do we remember what it was? It's way up at 40, eh? Yeah, it's way up here. There's our graph. And there's our beginning. And now we're going to set the 0 is equal to f prime of x. And it's going to draw it for me right there. Sure enough, it's 70. There's my fuel efficiency. And then if I punch in my f of 70, it's going to give that 35. If I take 35, I multiply it by 2, and I multiply it by $1.15, I get $80.50. That's my fuel efficiency at 70 kilometers an hour, and it's located right there, the lowest point. I could even draw y is equal to 35. That's the lowest point of the best fuel efficiency. That's the tangent slope of 0 right there. Right? You can even do f prime at 35. Sorry, at 30, 70 rather. And you're going to discover a slope of 0 right there. Okay, and you can make h of x equals that. And it should draw you, I don't know, it's drawing it down at the 0 line. Doesn't do much there. You'd actually have to take a, b values. So, for instance, since I know my x is 35, I could do x minus 35, and I know it occurs up at 35, x minus 70. It doesn't matter. You could draw a tangent line, and I'm not. I've gone too far. I've gone too far. But there you go. Desmos is amazing for you to understand all sorts of things. Now, notice these questions are the same thing over and over again. So the polynomial function has this. It has a certain range. Models the shape of a roller coaster track, where f is the vertical displacement of the track, y is the horizontal displacement of the track. Okay. So f, the result is going to be how high the roller coaster goes, and the x is going to be how long it goes. Both displacements are in meters. Determine the absolute max and min of heights. Derivative, it's the same thing. So I'm going to just jump straight to Desmos. What kind of graph are we dealing with? Probably a cubic, yeah, because otherwise you wouldn't get any bends in your roller coaster. We're trying to create a lot of bends in this one. What is it at 0? This roller coaster starts at 10. Did it put a limit on anything? Yeah, 0, small as they put this range on it. $75? Yeah. So boom, you can right away know that if you take your first derivative, you're going to end up, what's the derivative of a cubic? You're going to end up with a parabola formula, and you're going to find the two factors are x minus 20 and x minus 60. That's the two min and max points. You're going to plug in x is 20 into the formula. You're going to discover, oh, I got a max point. What's x of 20? You're going to discover you have a max point right there at 42, and then you're going to say, oh, what's f of 60? You're going to discover you have a min point over there. Is it lower than that? No. It comes down to the same level you started, which is great. Otherwise, your roller coaster would drive into the ground. Well, not really, because you started on this roller coaster 10 meters off the ground. If this went down below 0, they'd have to dig a hole for the roller coaster to go through, or like at some, they go through water in a tube, which is kind of cool but scary. And so this roller coaster goes up, reaches its peak there, goes down, reaches its peak there. It's 20 meters along the track when it hits this peak, and it's 60 meters along the track when it hits this peak. It's 42 meters off the ground and 10 meters off the ground. It's just taking the first derivative. It'll become a parabola, and you might say, oh, but it's going to have all these little decimals. You're going to discover that you just multiply it. So I'll take the first derivative for you just to show you. Just to show you how you get there. The rest you can do. Okay. When you take the first derivative of this, the 10 is going to disappear. And you're just going to be left with 0.003x squared minus 0.24x plus 3.6x. 3.6. So how would you solve that? Well, you're going to divide this by 0.03 every single term, so that you're left with x squared. And when you take this and divide it by 0.003, you're actually going to discover that it becomes 3 times 3 times 24. It's going to become minus 2. And then when you divide this by 0.33, you're actually going to discover that it's, it's 0.3. There's an extra 3. Okay, so let's take 0.24 and divide it by 0.24 and divide it by 0.003. Let's try that again, because I got the wrong thing that I had over there. 0.24 divided by 0.003. 80, that's fine, so I totally screwed that up, minus 80. And you're going to discover that this one is the same as 360. So how do you do it by hand? Okay, notice the decimal places. How would I get this decimal place to 3? I'd multiply it by 1,000. And so I multiply the top by 1,000, so you end up with 3,600 at top divided by 3, which is 1200. Let's see if I got that right. 3.6 divided by 0.003. 1200. Then you might say, oh yeah, don't forget that this is 3x squared, because when I divide this, oh no, it's just 1. It's just 1. So I've essentially factored out 0.003 from all of this. So that's a factored out, and that's how you'd factor it out, like that. And by hand, you just move the decimals over until you can divide it like that. So that's this, and when I factor this, I'm going to discover x minus 20, x minus 60. And sure enough, 10 times this, and 2 is 1200, yeah, and they add up. And there you go. When x is 20, I now plug it back in here to find the height of the roller coaster. And when x is 60, I plug it back in here to find the height of the roller coaster is 10. It's 1xb. And that's where just having Desmos verify it for me right here is a bit nicer. But as you can see, we don't, I'm not going to do it now. Part C gets into crazy stuff, and then you ask your teacher if he wants proofs and if he wants part C, because I'm not going to do the part C. Usually physics related. Graph the cubic function with an absolute, no, I'm not. So that just means the derivative at this point is going to be 0. And they're asking me for a cubic function. And it has a maximum at this 0. It has a local minimum at this 0. It has an absolute max. So it's telling me the absolute min, and locals just mean kind of, so this would be an absolute max, and this would be locals. That's a local, that's a local. That's an absolute, that's an absolute. Okay. Peaks and valleys of graph, and do not have an absolute extrema. Note, local max, mins, values occur at peaks, and valleys of graph do not have to be they don't have to be. What is the domain of this function? Well, that's interesting. Okay, so that means that, so min, let's start at the min. Minus 12, minus 2, comma, minus 12. And we're just going to have a dot. By the way, the domain is this to that. Oh, sorry, to that. So the domain is this, minus 2 all the way to positive 4. Because over here at 4, we got a 4, comma 9. Now, they tell me at 0, comma 3, 0, comma 3, there is a local max. And then they tell me at 2, comma minus 1, sorry, that's 0, comma 3 is in the wrong spot. And then at 2, comma minus 1, there's a local min. So let's draw it. Boom. Boom, boom, boom. We're dealing with a cubic, which means its derivative is going to be a square. It's going to be a parabola. And we're going to label this 0, comma 3, 2, comma minus 1, which means the derivative for this occurs when the slope is flat, occurs at x is equal to 0. And when I plug it into the original cubic equation, I'll get 3. But at x is equal to 0, we have a derivative of some kind that is going to be equal to 0 when x is equal to 0. So that's hard to understand. When x is 0, the tangent of this curve is also going to be 0. And when x is 2, the tangent is also going to be, slope of the tangent is also going to be 0. Which means when I take the derivative and I solve for x, I'm going to get these two things, x minus 0 and x minus 2 are going to be the solutions that come out to create the tangent. I don't know what it's multiplying it by yet, but I will soon. So that means if I expand this, I'm dealing with, obviously it's just x squared minus 2x, right? And I can only have two possible max mins for a cubic, and this is the formula of the tangent. However, I don't know what the multiplier is. I will soon, though. If this is the formula for the tangent, and I go backwards, I know I'm actually dealing with, if this came out as the derivative, I'm actually dealing with, so I ended up with x squared. So that means I started with x cubed, and the 3 came down, and it disappeared. So that means I started with x cubed over 3. If I ended up with minus 2x over here, it means the x started as minus x to the squared, and when the 2 came down, it became a 0. But I don't know what number I had, and it doesn't look like there's an x value, because there's no number in my derivative, so there's no x value, and there's a mysterious number here. Well, now I have roughly what my formula is, and I know that when x is equal to 0, it's going to be equal to 3. So when x is 0, it's going to be equal to 3. Well, that would be 0, and that would be 0, so this must be 3. Then I also know when x is 2, it's going to be equal to minus 1. So when x is 2 here, I get 8 over 3, and I get minus 4 plus 3. Minus 4 plus 3 is minus 1. So all of a sudden, it has to spit out as minus 1. So all I know is that, yeah, the result is 3 here, but there might be something multiplying this mysterious number. Let's call this mysterious number a. And I know that this multiplier b up front, b times a, is going to end up being 3. Okay? And it's also going to have this multiplier up here, and this a here. And I also know that b times a, and does that make sense, is going to be equal to minus 1 when these things exist. So when it's 0 here, b times a is equal to 3. But when b times all this stuff, it's going to be equal to minus 1. Now I have two equations. So I have 8/3 8/3 b minus 4b plus a, so a I don't know, is equal to minus 1. And then I have b times a is equal to 3. So I can replace my b anywhere I want with a, with an a value that I get from here. And or I can replace my a value with a version of b. I'm going to choose to rearrange a as 3 over b. And everywhere I see b, I'm going to replace it with my new a. No, I'm not going to. I'm going to rearrange my b into my a into 3 over b. And I'm now going to get this, 8 over 3b, and I'm going to substitute it in there. Minus 4b plus 3 over b is equal to minus 1. I'm going to multiply everything by 3b. Hope this works out. Multiply everything by 3b, and here I get cross, cross, I get 8b squared minus 12b squared plus 9 is equal to minus 1. 8b squared minus 12b squared is minus 4b squared is equal to minus 10. B squared is equal to 10 over 4, so I probably made an arithmetic error somewhere, but we're going to try it anyway. So b square root, I don't know, but I think I was close. I think I made an arithmetic error somewhere. I just know that b times a is going to be equal to the low value, which I believe was, no, the big value, which is going to be 3. Because x is 0 there, so all the x values disappear. And I also know that b times when x is 2, when I plug it into my equation that I figured it out, what was my equation? It was x cubed divided by 3 minus x squared. And when I plug in and then it's plus a magical a in there. When I plugged in my 2, I got 8 over 3 minus 4 plus my magical a. All is equal to minus 1 when multiplied by b. And that's how I came up with this. That's what I'm missing. So when I replace my a value with 3 over b, I get 8/3 b minus 4b plus 3 over b times b, which just becomes plus 3, is equal to minus 1. When I multiply everything by 3, I get 24b minus 12b plus 9 is equal to minus 3. 24 minus 12b is 12b. 9 to the other side is minus 12. b is equal to minus 1. I know that b times a is equal to 3. So therefore b is minus 3. Or sorry, a is minus 3. Which means that the equation is minus x, if b is minus 1, and a is minus 3, the equation is minus 1 times x cubed over 3 minus x squared minus 3. I'm going to plug this into Desmos. And I'm going to see if I get I'm going to put the limitations on it, minus 2 to 4. Okay. I'm going to zoom in on it. And I'm going to see if I get my max. Yep. Oh, so I made an error, because that is supposed to be down here. But I did get that. So let's just see what happens if I change that to plus 3. No. So that doesn't work. Let's just see if I change this to 1. No, that doesn't work. So minus 1 is the only way I get this to here. And that's the only way. I probably solved the derivative incorrectly. Because to get that down to there, I believe it probably has to be like that. And maybe it has to be 1 over x. No, that's not going to work. Yeah. So I probably solved the derivative incorrectly, but that's correct of how to go about it. Let's go back to see the derivative. So since I know it has a local minimum point, here when x is 2, I know local maximum when x is 3. And I know the slope there when x is 0. The slope is going to be 0, and when x is minus 2. Sorry, when x is 2. So I know that this formula is true for the derivative, and we just don't know what the multiplier is. So I get x squared minus 2x is the formula of the derivative. Oh, there we go. So how do you get x squared with nothing in front of it if you started with x cubed? No, you'd have to divide it by a third, or have a 1/3 multiplier. How do you get minus 2? If you started with x squared, it would have to be minus x squared. Maybe that's where I made my mistake. Nope. And it's all going to be multiplied by something to equal 0. And the question is, what do you multiply that when x is both 0 and 0, when this is that and this is that? Maybe I could just use the tangents, actually. So, when will a number times 1/3 x cubed, actually let's go back to the derivative, when will number x squared minus 2x, when will that equal to 0? When x is 0 and when x is 1. Now I already solved that. And then what number will this multiply out and equal 3 and equal to minus 1? And right away, when x is 0, right here, it's 3. So the product that this multiplies here must be equal to positive 3. That's how I got b times a must be equal to positive 3. But down here, I'm going to have b, and just make it plus a, times a, and the whole thing's going to come out as minus 1. Okay, so that makes sense. So far, so good. So b times 1/3 x cubed minus x squared plus a mystical magical number is going to be equal to 3 when these are 0. So that's how I get b times a is equal to 3. Then, when x is 2, we get x squared. X cubed. 8/3 minus 4 plus a is equal to the mystical minus 1. Those are the two equations I'm working with. So for this one, I get 8b/3 minus 4b plus ab is equal to minus 1. That's what this spot is. And I also get b times a is equal to 3. If b times a is equal to 3, and b, or a, is equal to 3/b, which means I can replace that with 3/b, I get 8b/3 minus 4b, and this resolves to 3 is equal to minus 1. When I multiply everything by 3, I get 24b minus 12b plus 9 is equal to minus 1. When I resolve that, I get 12b is equal to, there we go, minus 10. So b, is that right? Let's make sure I did that. 3. There's one problem. That's just 8b. So I get 4b is equal to, right there. When I multiply everything by 3, I get 8b minus 12b plus 9 is equal to minus 1, or is equal to minus 10. 8b minus 12b is minus 4b is equal to minus 10. So b is equal to 10/4, or 5/2. For this to multiply a to equal 3, a must be, how do you get something to equal 3? The reciprocal, you'd have to multiply by the reciprocal. So if b is 5/2, you'd have to multiply by 2/5 times 3, which is 6/5. 6/5. So that cancels. Sorry, these cancel, and this goes into that 3 times. So 6/5. So now a is equal to 6/5. B is equal to 5/2. Boy, that's a big difference. Let's see if I got it right. What did I say a was? 6/5? Yeah. way off. It's totally, it's got to be plus, sorry. Oh, now it's still off. So it's just a calculation error somewhere. I'm not going to do it again. But that's the idea. You have to work backwards and then solve for your two unknowns. And just keep in mind that you can figure out the a times b is definitely going to be equal to 3 right here. But I'm doing some sort of calculation error wrong here. And it's just being tired. Certain manufacturing process level of production exchange the cost of production is this for this range. What level of production will minimize the costs? When u of x, cost per unit, definitely not going to do it. Definitely not going to do it. So you got a mid-chapter review. It's a very good idea to take it. And this is just all about optimization. Now the good news about optimization is it's usually about cost, right? And cost often comes down to a maxima. So that's your usually max profit, and it's often an x squared. You just have to derive the formula for the cost. They're going to give you something like 5,000 people can fit into a bus and pay $20. We learn that for each person, each time we raise that by $1, we lose 400 people. Then you have to resolve this, and that's going to equal to the profit, and that's obviously it's going to be like an upside down parabola, and you're going to have to figure out the max profit, what x, and then once you figure out the x coordinate, you got to go back in here and figure out the cost of the ticket. This was a long effing video, and I'm sorry.